guess we can. Yeah, we can start. So, do you have questions about the project? No. All right. Okay. So, just a reminder: there's no class on Thursday, but there will be class next Tuesday. Okay. So let's. All right. Okay, so we've talked a lot about numerical methods, how to solve equations, what the governing PDEs are, where they come from, the conservation laws. But it's very important to know the limitations of simulations. What is the best you can do? What are the things that are not feasible? Okay. All right, so that's where we start with. What is turbulence? So what is it? What is your definition? Just give me a general definition. It doesn't have to be scientifically correct. When I say turbulence, what pops up in mind?
My thinking behind it is it's when fluid kind of overcomes its internal velocities, slipping around each other to create a spurious motion.
Okay, so instead of nice regular flow, you become sort of chaotic and you become unpredictable in what sort of motion you get, right? What's your definition?
Kind of the same thing. I just think of on the plane when we hit turbulence, you're shaken, so it's not a smooth velocity or.
Yeah, so that's, if you talk to any lay person and you say turbulence, that's the first thing that pops up in mind, right?
Yeah.
Oh, plane, turbulence, shaking. So these things are related. As you said, the flow becomes chaotic, non-planar, and that's what causes vibrations on the air. Okay. But in fluid mechanics, this has a very specific meaning, and we'll talk about how it all started and where it all has been going. There has been no end yet. I don't know if there will be. Okay, so turbulence happens at very high Reynolds number, so at very high Reynolds numbers. The exact instantaneous solution of Navier-Stokes cannot be predicted exactly. Well, cannot be predicted a priori. Okay, so just take a second to think about what this statement means. If we think about very simple heat diffusion problems, so we have a rod, we heat one end, we heat the other end. We can predict exactly where the solution will go, how it will behave. Right? Again, we're lucky in that the equation is linear, we can solve it analytically. But when we start talking about the Navier-Stokes equations, there is a term that is nonlinear, which means it's difficult to come up with any analytical solution, right? But that's not the end of it. It actually turns out that even if we do simulate the flow or do an experiment, you cannot predict a priori what the exact instantaneous solution will look like. Okay? And again, we'll come to that slowly. What exactly does that mean? So first, Reynolds number. What does the Reynolds number mean? RE equal rho U d by or U d over mu, right? So what does this represent? It's a non-dimensional number, fine, but why? Why do we care so much about this? Do you know physically what this number gives us an idea of?
Ratio of convection terms to viscous terms.
Yeah, exactly. So this is a ratio of inertial forces over viscous forces. Okay, and let's write down the momentum equation. Okay, so in here, this is the viscous term, this is the nonlinear convective term. So this ratio, the Reynolds number, is just telling us which term is more important. If it's high Reynolds numbers, the convective term becomes much more important than the viscous term. And if the Reynolds number is very, very small, it's the opposite. Viscous terms are much more important. Okay? So now, do you remember what is the only source of energy destruction in this equation? So there's one sink of energy, which is?
The viscosity?
Yeah, it's the viscous term. So this is the only physical term that can destroy kinetic energy. Okay, if we took this term out, you know, the total kinetic energy of our system would be conserved. It would neither go up nor down, assuming that the system is isolated, right? So this is the only physical term that can destroy kinetic energy. So it's well, and how? Do you remember how? Physically, you know, if you were to explain to a layperson, what would you say?
It's like friction.
It's friction, and it converts kinetic energy to
Potential or heat energy.
heat. Yeah. Okay. So yeah. So converts it to, well, let's say dissipates kinetic energy to heat because it is friction. Okay, fine. So the Reynolds number basically tells us which one's more important, the viscous destruction of energy or the nonlinear convection. Okay, and let's say at high RE, much greater than 1, let's say on the order of 1E7 or 1E8, what is this telling us? This is telling us that viscous forces are much weaker than convection. Okay, and if we go by the ratio, you know, this is just saying viscous forces are 1 minus 7 times the convective inertial forces. Okay. So what will happen in this scenario? If I introduce a small perturbation to the flow, what do you think will happen? So let's say I have a nice flow field that let's function x. Okay, and then I come in and jolt the system. I put in a small disturbance over here. Okay, let's say that so that's at a particular time instance. I come in and perturb the system this way. What will happen? Let's talk about the opposite case. If the Reynolds number were very small, viscous forces were very large, and I come in and put in a perturbation, what would happen?
It would propagate and dissipate.
It would propagate and dissipate, all right? And if viscous forces are extremely large, these perturbations will get killed off almost immediately, right? So they will get smoothed out. But for high Reynolds number cases, the viscous forces are very weak, so they cannot smooth out this perturbation immediately. So this persists for a very, very long time. Okay? So in this case, what happens is perturbations and instabilities can persist for a very long time. And this can happen even when the perturbations introduced it's minuscule. Okay, and it turns out that even small perturbations can actually grow very quickly because there's nothing to stop them. There's nothing to stop their growth. And maybe now you get a sense for why it's so difficult to predict the exact velocity field at high Reynolds numbers. And very small imperfections in your experiments or very small imperfections in your simulations can, grow into something you cannot predict accurately. Does this make sense? Okay. And again, slowly we're coming to the point why all of this is important. How does this influence our simulation? Okay, so, the number is called Reynolds number, so let's see what Reynolds did to earn his Osborne Reynolds. Right. All right. Okay. So what Reynolds was doing basically was this. There was water flowing through a thin pipe, and he injected ink or dye into the flow. Right? And he noticed that if the Reynolds number, which did not exist at the time, if the velocity were small, you would get a nice laminar flow. If he increased the velocity, the flow would get disturbed, and it would result in a very chaotic mixing of the dye in the water. Right? Do you believe this? Why do you believe this? Why would you believe that it's laminar? You're injecting one fluid into another.
It's moving really slow.
Yeah, if it's moving really slow, any disturbance that happens at the interface quickly dies out because the viscosity is so high. Okay, and this actually happens. Let's see if we can find. All right. Okay, so Reynolds number is 355 right now. You see, this is actually in motion. So there's all right. Something got disturbed. And see, as they pump up the injection velocity for the dye, now we see that even small perturbations, they start to grow. And they will grow very rapidly as the Reynolds number increases. Okay, so what's the benefit of this? It seems it's a terrible thing. We should, all be afraid of this. What's the benefit of having high Reynolds number flow? Yeah.
Mixing.
Mixing, all right. Can you explain, give us a few examples?
If you are adding any solvent that you actually need to be concentrated at a uniform rate in a fluid, then turbulence is good for you. Like if you're adding something into the water in the pipe flow, which has to be uniformly distributed in the water, then mixing is good for you.
For example, what would you want to mix evenly?
Any like paint or anything that is put any solvent that is or any
So
any organic fluid, yes.
Exactly. So when you make paint, you want all the pigments to mix together nicely, but they're very viscous, so you have to do it at a high velocity. Right? Otherwise, they will not mix, as you saw. Okay? And I will pull up another video where you see it's actually reversible if the Reynolds number is very small. Okay? So paint was one example, and in the chemical industry, this is a very important problem. Mixing is essential because any chemical you make, you have to mix different constituents until you get the product you want. In combustion, right? What are we mixing? In our cars, we're basically mixing air that's injected into the engine and fuel. And they should be mixed well, otherwise we'll just throw them out through the exhaust before they burn completely. If it's not mixed well, the fuel will not burn. Okay. So turbulence is very important, right? So that's a big advantage. Advantage is...
You're still on the computer.
Oh. It enhances mixing. Okay, and this can be important in chemical industries, in making pharmaceuticals, and in combustion. Let's see, more examples. As you said, let's see, air fuel, mixing, or efficient combustion. So there's many reasons that we might want turbulence to be present. Right? But many times it's actually a disadvantage. Can you give me go ahead if you can think of anything.
Increase of drag.
All right. Why do you say it increases the drag? Does anybody know why it would increase drag? Drag on what?
Yeah. So it will transport the low momentum fluid near the wall to the fluid which is at high momentum. So they were reducing the momentum for the high velocity fluid, and then that results in like drag.
Yeah. So that's actually another way where turbulence is mixing things. Okay. So if we have flow over a wall and you said that the flow becomes all chaotic, right? And it starts swirling. So what happens is the slow-moving fluid over here gets ejected up, and it slows down the fast-moving fluid. So that's basically creating drag, right? So let's see. So this generates drag on vehicles, anything that moves through air or water, okay? Not in space. All right, so it can be airplanes, cars, ships, you name it, whatever. Okay. And you know, it does this, but why don't we fix it? Why don't we do something to get rid of this drag? What would you do if I told you minimize the turbulence on this car that I want you to design? You would make it a very solid block of rectangle, put wheels on it, go. There are cars like that, right? There's the BMW one. What is the boxy one?
The G something, G-Wagon.
Yeah, so, you know, will they get an A+? No, it's terrible because they are doing exactly this with all those sharp edges and, you know, a sudden change in geometry. You create a lot of drag because of this and because of flow separation. So the main objective whenever you design these things is to make them aerodynamic. So the shape has to be such that the flow experiences the least amount of obstruction. But there's only so much you can do. This, you can never get rid of this. Again, why? Because the Reynolds number is so large that no matter how nice you make how smooth you make the flow, some small perturbations will always be present, and they will trigger this. So we can minimize this by try to minimize drag by using aerodynamic shapes. And this helps in many ways. It reduces the pressure drag and also reduces the amount of turbulence. All right. Think in terms of something that's very important to us here in Florida. What happens from August to November?
Hurricane season.
All right, so give me more. What's the, okay, so think about the Reynolds number. What Reynolds number is U times D over mu. For storms and hurricanes, what is the typical speed? Let's say 10 meters per second, which is very fast, right? What is the D? Typical length scale? A few kilometers? Let's say 1 kilometer, okay? So 10 to the 3 meters. And this mu for air is 1e minus 5. So already our Reynolds number is on the order of 1e8, 1e9. Okay. So you can imagine how negligible the viscous forces are. Okay. And again, at very high Reynolds numbers, it's very difficult to predict what's going to happen. All right. So now, give me your answer.
The weather prediction?
Yeah, weather prediction cannot be done accurately for a long duration, exactly because of this. Okay. Turbulence influences the weather and makes forecasting difficult. For more than a couple of days. Okay. You know, you can predict what will happen tomorrow, maybe what will happen the day after tomorrow, but after that, don't bet on it. Okay. So it might say sunshine or rain. You never know. Tomorrow you can trust, more or less, and there's reasons for it. Okay, so those are very big disadvantages of turbulence, and this is very important because it's necessary for evacuating certain areas or preparing for the oncoming storm. All right, so okay, we have roughly an idea of what can be the advantages and the disadvantages. So that's why this has been a very active field of research, because even now we don't have a very good idea of how to model this. The only way we can figure out what the answer is, either run an experiment or run a simulation. And again, simulations are limited. We'll come to that. Okay. So we've talked a lot about, all right, things are not predictable. Let's go to the other extreme first, just to see what happens. Okay, let's talk about Stokes flow. So what is Stokes flow? Have you heard of this before?
Yes. Rain.
Okay.
Low rain, very low rain is low.
Yeah, it means the Reynolds number is very, very, very low. All right.
Yes.
And so the equation looks like.
There are no reasons.
We have our du by dt plus u dot naphtha u minus naphtha p by rho. Which term is very small and negligible?
The convective term?
Yeah, so we'll say this term can be kicked out, all right? And we can also say, all right, we will look at steady. All right. So what happens in the end is we get now the p equal nu rho is mu, now the squared u. Okay. And continuity is lambda dot u equals u. So these are the two equations that we need to solve. And you can see this is the steady state solution since we zoomed. All right. And this actually has some sort of analytical solutions. It turns out that Stokes flow is reversible in time. Have you heard of this before? No? Okay. Let's see. One of the best experiments is to look at Taylor-Couette. Did it say Taylor-Couette? Taylor-Couette flow. All right. Yeah, perfect. Okay. So the setup is basically
Putting in red.
you have two cylinders. There's an outer cylinder and there's an inner cylinder, and there's fluid in between. And it can be glycerine or something, high viscosity like that, right? And Couette flow is basically what the flow looks like when you rotate, when there's relative rotation between the two cylinders. Okay. Is the setup clear? So you have an inner cylinder, outer cylinder, both might be rotating, or only one is rotating. The fluid doesn't care. It just cares about relative rotation. Okay? And what you do is, with a pipe, you come in and you inject dye in the glycerine that's in this container. You inject a red dye, you inject green dye, you inject blue dye, and then you start rotating the inner cylinder, the one over there, slowly. Right? See, there's a knob, and the fluid in between the two cylinders is moving. Okay, so now we are mixing the different dye globs, and now they're gone. We can no longer recover them. True or false?
What was the question?
The 3 dots of dye, they're gone. They don't exist anymore. True or false?
As I can see, yes.
As you can see, yes, right? There's no way I can recover the dots, right? Okay, so he's rotating clockwise right now. Okay, right? He's gone a few turns, let's say 4 or 5 turns. All right, at some point he stops and starts to going backwards. There's no way the dots will reappear. So, Photoshop?
Maybe.
No, let's see. So this is the final condition, and where was the initial condition? The initial condition was this. Not Photoshop. Okay. You didn't know this? No? Okay. Yeah, it's a very simple experiment, and this is Reynolds number very, very small, much, much smaller than 1. So you can see viscous effects are strong enough here to prevent excessive distribution of the ink globs. And the equations are time reversible because there is no time here, right? So the solution does not care what happened in history. It only cares what the boundary condition looks like. Does this make sense?
Well, mathematically, we assume it's a steady state, but the experiment is not a steady state. It's
Yeah, you can keep the du by dt term here.
you know, that justification with mathematical, this equation, I think this is not a good for that phenomena.
Okay,
Because
mathematically, this is the equation for what? Is it the equation for the ink, or it's the equation for u, right?
yes, it's for you.
So if you give me u of outer cylinder and u of inner cylinder, I can give you the exact u anywhere in the domain, in between. I do not care about what happened in time before, what's going to happen next. That's all this means. Make sense?
But we didn't consider the first term. We assume it's steady, but it's not steady.
What is not steady?
The experiment.
Is there any change in velocity after the initial start?
First of all, the initial start is one thing. The
Fine.
second is then it was counter-rotating, right?
Right?
So definitely there is a unsteadiness when it's counter-rotating.
That's what I'm telling you. So, of course, you cannot start from something, right? So, once it has started and you're not accelerating, you give me the u of the inner cylinder, I can give you the u from inner cylinder to outer cylinder, exactly. I don't need to know what happened 1 second before. In turbulent flow, you cannot do this. That's the point, okay? In turbulent flow, if I say at 1 second the flow field looks like this, what will happen at 2 seconds later, can you give me exactly the answer? You cannot. You have to go slowly, you have to simulate, okay? And another thing is in Stokes flow, if you redo the experiment 10 times, you will get the same exact thing. In turbulent flows, you are guaranteed to not get the same exact thing. Okay? If you repeat the same experiment, the flow will look completely different. Make sense?
Yes.
Okay. So, this is time reversal. And you can go look at Taylor-Couette experiments.
I think it's Cote, right? Or
No, Cote is a guy who does kinetics. Taylor-Couette experiments at high viscosity, okay, or low velocity. Okay, so we saw that Stokes flow is reversible. Okay. And that's the other extreme. Most of our problems occur at high velocities. Alright, so let's see. Actually, so let me pause here for a bit and everybody who's registered, could you please fill out the spot survey, which is, so spot for people who are attending for the first time is just your feedback to us, so we can improve the material in the course, improve the way we teach, etc. Right? So you can just log in to spot.fau.edu, and I will go out of the room for like 2-3 minutes, and you can do it on your cell phone or your laptop. And if you're watching on the video at home, please do this if you can. So it's just spot.fau.edu. Okay, so you can log in here with your username, and I will be back at 11:45, let's say. Okay. All done? Right. Okay, so let's see, where were we? All right, so let's see. So we talked about with low Reynolds numbers, the flow behaves in a strange but very nice way. It's very predictable and time reversible. With high RE, we have the exactly opposite problem, which is instantaneous you cannot be predicted exactly, even if you repeat the same experiment or simulation. Okay, what does that mean? So let's see. Let's look at Turbulent Flow. Oh, by the way, if you don't know this book, it's called An Album of Fluid Motion by Milton Van Dyke. It's very nice. It's got illustrations of a variety of flows, right? So here is what one particular turbulent flow might look like. So we have uniform flow coming in, and there's a grid. So we just have a two-dimensional view. So this is a three-dimensional grid which perturbs the flow. And you can see that the nice clean lines, so this might be smoke or dye that you have injected upstream. The nice and clean lines get disturbed, and very soon they become completely unpredictable and random seeming. Okay. So this is exactly what turbulence does. If it were Stokes flow, these nice clean lines would stay straight. Okay. All right. So why does this happen? Why do the nice clean lines do this? Remember, this is very high Reynolds number flow, and what did we say happens in high Reynolds number flow?
Any perturbations can persist for long times.
Yeah, perturbations persist for a long time, and they actually grow. They grow, they merge, so that's exactly what you see happening. Perturbations caused by the grid are growing. Okay. And let's say that I put a velocity probe over here. Velocity probe can be a pitot tube or a hot wire anemometer. If you don't know what these things are, don't worry. There are ways to measure experiment with the velocity experiment. Okay. So you put a probe over here and you plot the signal of velocity over time. What will it look like? So it might look like if you plot it over time, sitting at a point, the velocity might look something like this. Right? So it looks like random noise with a very defined and constant mean value. Okay? I turn the experiment off and restart it and measure again for the same time interval. What will happen? At the same location. Everything is identical. Nothing changes. There's nobody in the room breathing, nothing. What happens?
The average will be the same, but it'll look different.
Yeah, that's exactly what happens. That instantaneous curve will look completely different, and you have no idea what it will look like, right? So the curves will not match. But the mean, assuming you haven't changed anything in your experimental parameters, the mean will not change. The standard deviation of the fluctuations will not change. Okay. So this is, again, this is assuming that you let the flow evolve and now everything is statistically stationary. This term means the flow statistics have become steady. And this can include the mean, the standard deviation, and even higher order statistics. Okay, but if you understand this, that's basically what turbulence does. No matter whether your experiment is exactly the same or simulation is exactly the same, you can never reproduce the instantaneous velocity. This doesn't make sense. Why should this happen? If I have the same exact experiment, why should there be any difference? Why? It's the same wind tunnel with the same inflow, the same fan, nothing changes. Why this thing?
Because that fluctuation is like noise is random.
Where is the noise in your experiment? You have taken every care.
No, I don't mean it's because of the noise. This is similar to what happened for the signal and noise. That's what we have for velocity and that fluctuation, the tips there.
Yeah, but you're talking about noise, but these are governed by physical laws.
Yes.
Very strict equations.
Okay.
Boundary conditions are the same, initial conditions are the same, everything is the same. Why would the answer be different? Again, we've talked about this, you've told me this, but in the experiment, where is it? So you said the small perturbations can change the flow field, right? In the experiment, where do these perturbations come from? For example, if you're doing this in the hydro lab, where is this perturbation coming from?
That comes from the, for example, environment.
Yeah, if you're running an experiment with a flow,
Noise.
the floor might be vibrating because there's a truck outside passing by. There's very small fluctuations in the air, okay, which, extreme. But even the experimental setup, the plate is not perfect, right? The surfaces are not flat, they are not 100% smooth. On the molecular level, they are very rough, okay? So that's another source of perturbation. So this happens because very small perturbations, so on the order of 1e minus 8, 1e minus 16 can trigger this, okay? Okay, fine. The experiments are imperfect. What about simulations? In In simulations, you have a perfectly smooth wall. There is no molecular imperfections.
I think that those errors, truncations error, that those small
Numerical errors will be, they're not noise, right? They're exactly determinate. Correct? So the errors you're making are determinate.
Yes.
They're not random fluctuations. But in simulations, this happens. Why? Go ahead. I think we lost you.
The machine errors,
Machine error. What is machine error?
like the computer, it itself generates some order of accuracy. So that might be different for different runs.
All right, you're saying the machine has some order of accuracy. What does that mean? Can you explain a little more?
Yeah, so depending on how the system is performing at some moment of time, like what all processes are running on it, it can give me uh, different results. Like if I have a number 2.30896999, it can give me 8 instead at the in place of 9. So that's some sort of error.
Yeah, but you're talking about error-prone computing. I gave you a perfect computer, this will still happen. Perfect computer in the sense that there's no hardware issue. Not one hardware affecting another component. Okay. So, are you guys familiar with, maybe I mentioned this before, machine precision? Have you heard of this before? So the arithmetic that we do on the computers is not infinite precision. What does that mean? It means that, for instance, if we do double precision, the smallest number we can represent on the computer is
1e to the negative 16.
1e minus 16. Single precision is
1e to the negative 8.
1e minus 8. This is also called float. Okay. So, on the computer, any number can be represented up to 8 decimal places with exactness. Okay? And if I say this number is single precision, and then I try to add 1e minus 12 to it, what will happen?
It'll stay the same.
Yeah, so up to the 8th decimal, it will stay the same. After that, you have no idea what will happen. Okay? The 9th, 10th, 11th, 12th decimals will keep changing every time you hit enter. Okay? So that's a random source of error. And this is assuming that the hardware is perfect, unlike what you were talking about. That can also happen, but machine precision is the problem, all right? So why do we limit ourselves to single precision or double precision? Why not go quad precision or oct precision?
To conserve RAM.
RAM, yes. So to store this single precision number, if I need, let's say, 100 megabytes of RAM, to store double precision, I will need exactly double on that. To store quad precision, I will need 4 times that. So we always have to make a compromise between precision and RAM, accuracy and RAM. Okay. But again, it's not, there's no point having infinite precision because this is what happens in reality. In nature, you always have environmental perturbations which will cause this to happen. So our goal is not to match the curves exactly. As long as we can predict statistics, we would be happy. But even that we cannot do. Okay? At the moment, if you give me the Reynolds number is 20E5, what will be the standard deviation of velocity? I have no idea. I cannot tell you. There's no models that exist for that. Okay? And that is one of the very big problems in fluid mechanics. Okay, do you have questions for the moment? All right. Okay, so turbulent flow is clear. What does turbulence mean? It means the instantaneous velocity field is not predictable, because very small fluctuations can change your flow field completely. Okay, and this is the basics. Now, if we go into a bit more detail, what does this mean physically? Okay, so then it's time to talk about energy cascade. So let's look at the environment again. So let's consider an atmospheric flow, where we have an eddy the size of 1 kilometer, let's say. What will happen to this big eddy in the atmosphere? It will keep going, turning forever and never dissipate.
It'll dissipate.
It will dissipate. It will dissipate immediately, something else will happen.
Something else?
What?
It will mix with other atmospheric eddies.
It will interact with other atmospheric eddies? Yes, true. It will interact with other eddies of its own size or smaller sizes. But let's assume it's an isolated atmosphere, right? And it has only one big eddy. What will happen to it?
They separate to small,
Yeah,
small and small, and then decays.
true. And why does that happen? Let's say Reynolds number is only order 1E7, okay?
I think it's fluid instabilities. That's
Exactly.
Kelvin
So
Helmholtz instabilities.
there's many types of instabilities that will show up here, okay? All of these instabilities, what they will do is they will break up the nice big eddy into smaller eddies. Just like the picture we were seeing earlier. Nice straight lines break up into chaotic flow. So this will break up into smaller eddies. Okay, and the eddies will generate even smaller eddies until we go all the way down to something, right? So initially this breakup is invisible. Due to, as you were saying, due to instabilities, growth of instabilities and perturbations. What happens once you get small enough is the Reynolds number will get close to 1. Right? Why? Because Reynolds number is UD over nu. The local Reynolds number. So we're talking about a 1 kilometer sized eddy over here. Maybe its speed is 10 meters per second. Nu is constant for air. Over here, we can be 1 millimeter. And its U can be a few millimeters per second, and U will be very small. So you see the Reynolds number changes with the length scale we're talking about. What will happen here? for these eddies.
You'll start to have viscous dissipation?
Yeah, exactly. So as the Reynolds number gets closer to 1, viscous dissipation will start basically destroying them. And this is a very simplified picture of how turbulence works. You have things that appear at large scales, and this might be because you have a car moving through air, which creates this large scale eddy, not 1 kilometer, several meters. And this will slowly break down until it reaches, until the eddies become so small that viscous dissipation can kill them off. The same thing happens in aircraft. When you have a plane taking off, a huge plane taking off, it generates very big eddies, okay? And you cannot allow a small plane to take off for at least a few minutes because these have not dissipated yet. So these huge eddies will slowly break up and then dissipate. Okay? And you know, for the larger planes, the eddies are small enough that they can overturn a bus, and this tiny Cessna planes will, yeah, it's a very dangerous situation. Okay. So what is the scale separation we're talking about here? Physically, do you agree that all the length scales starting from here to here are important? Think about what will happen if we get rid of these. What will happen if these did not exist? Small eddies with Reynolds number read more or less 1.
Medium eddies would just continue their momentum?
Yeah, the medium eddies would just keep existing. They would not break down anymore, or you know, they would not dissipate their energy, because again, the Reynolds number is not small enough yet. But if there's a mechanism that keeps pumping in energy at the large scales, your system will eventually get saturated with a lot of kinetic energy and blow up. Right? Physically, that does not happen exactly because it gets dissipated. But in simulations, you're not restricted by anything. You can get rid of these small scales. Okay? How do you do that? If I say simulate a domain that's 2 kilometers in size, square, and put in an eddy of 1 kilometer in size, you know, at the initial condition is only this thing exists. Our expectation is that over time, these all will develop. What do you have to do? I've just given you 2 kilometer by 2 kilometer. What's the first thing you do? For doing any simulation, what's the first thing you do? Not clear? Okay, so, okay. Think about your project, right? So the project just said the velocity is cosine x times sine x, something, something. What's the first thing you do in MATLAB? Create a grid. Okay. When you create the grid, you have to pick. What do you have to pick?
Grid size?
Grid size. How are these eddies related to the grid size?
If they're too small, they can't be resolved.
Yeah, if they are very small, you better pick your grid size to be small enough that you can capture these. If you cannot represent this on your grid, you're basically doing this. You're cutting all of them off. Okay? And what will happen to your simulation if you don't resolve the dissipating scales?
To just continue to add energy. So,
Yeah, you keep pumping in energy at the large scales. There's nothing that dissipates. What we talked about right now, right? Eventually, all the energy will pile up at these eddies, and the simulation will go unstable. And that's exactly what happens at very high Reynolds numbers. If you use a good scheme, if you use a crappy scheme, there's numerical viscosity, which basically kills your kinetic energy. Okay? So that's exactly what turbulence models try to do. They try to say, okay, I will let you resolve only up to a certain length scale, and everything that is not present in your simulation, I will give you a term which will recreate its influence on the larger scales. Okay? So that's what turbulence modeling is. We'll talk more about it in detail, but is this clear how Reynolds number and simulations are related? Okay, so fine, simulation. All right, so here, actually, let's do a quick one. 1 kilometer to 1 millimeter. What's the scale separation?
1 e to the 6.
Scale separation is 1 e to the 6. Okay, and if I told you I want my domain to be 2 kilometers by 2 kilometers, what does that mean? What's my delta x?
To resolve small cities?
Yeah, if you do a simulation, your idea is to do it as physically accurately as possible. So,
Less than a millimeter?
so at least a millimeter, right? 1 e minus 3. What is the number of cells in X that you get?
Two e to the 6?
2 kilometers over 1 e minus 3, 2 e to the 6. 2 million points in each direction. In a real simulation, how many directions?
3.
How many n total?
Like 8 e to 18?
Let's say 1e90. Okay? What is the biggest simulation that has been run to date?
Around 8096 cube or 4096 cube grid points total.
Yeah, let's do that quickly. Let's see how many is that. So let's say 10,000. Okay? 10,000 cubed is what? 10 by 15. Correct or not?
Yeah.
1e15. Okay. So doesn't seem like a big difference, but it's 4 orders of magnitude off. And this is basically throwing a whole electricity generating dam at a supercomputer and letting it run for a day, a month or so. And in a very simple, nice configuration. It's called homogeneous isotropic turbulence. I will show you next time. So you can see with anybody who tells you that, oh yeah, high Reynolds number flow, we can do simulations, we can do modeling. either they don't know what they're talking about or they're trying to, hide something from you. So just remember that. Simulations are very useful, but everything has limitations. Okay, simulations have limitations. Why don't we just do experiments? Right, that's an important question. So simulations have these restrictions. Why not just stick to experiments?
So for 2 kilometers, you want to experiment every, at 1 millimeter, you have the data? This is
Fine, not 2 kilometers, let's say something smaller. 1 meter by 1 meter.
that is doable. I mean,
That is doable? All right, wait 1 second, go ahead.
Yeah, even the small time scales and length scales, they will be very difficult to be resolved in experiments. The instrumentation will be limited to resolve those things.
All right, let's ask.
it depends. What is the length scale you're talking about?
All right, so let's see. If we're talking about a 1 millimeter by 1 millimeter tunnel, okay, and RE is, let's say, 1 million, which is not out of the ordinary, okay? The length scales you would need to resolve, again, would be on the order of, L smallest would be on the order of 1 millimeter. Or, that's too large. That's the best I will give you. It will probably be 100 times more. Okay. So even with experiments, this issue of resolving the smallest length and time scales does not go away. The way you measure things in experiments is either you put in probes or you illuminate the field with a laser sheet. And then you can record the velocity, right?
It's doable, but it's expensive.
It's very, very expensive. This is again.
From 2 meters, yes. 1 millimeter. Millimeters means.
Yeah, you have to record.
Repeating a lot of. Yeah, recording.
You have to record in 1 millimeter squares for this whole 1 meter by 1 meter, and you have to record it. Time period might be 1 megahertz. This number I'm just giving you an example, right? This might not be fair. So you might have to record it at 1 megahertz. It's not just the smallest length scales that matter. It's also the smallest time scales. The vortices move at a certain velocity, so they have some time scale associated. So even with experiments, it's extremely difficult to capture data at very small length and time scales. Even if we do a laboratory experiment, forget about weather prediction, kilometer by 2 kilometer. Again, this is a very small, real area, whether cells are tens of kilometers across. Okay, so turbulence is a big problem, no matter whether you do experiments or simulations. And next class, I will talk about what people have been trying to overcome these issues. So turbulence modeling and where we are at the moment after 60 years of research. Okay, Thursday, no class. If you have questions about the project, again, email me.